Okay, well, hi everyone. I will start with some good news, with what may be some good news for you. There is absolutely no code in this talk whatsoever. This talk will not teach you anything about programming, and I'm sure you're deeply grateful for that by this stage of the conference. Yes, the title of the talk is it's DNS Gym, but not as we know it, which is actually a title I've shamelessly stolen from one of my work colleagues. And what I'm going to be talking about today is primarily, or put it another way, RFC 8484, DNS over HTTP, which you will notice was even in the title, abbreviated to DOE, because nobody could resist. And it's a means, this RFC appeared last year, as you can see. We're talking pretty up to date here. It's a means of doing DNS queries over HTTP, or specifically HTTPS. But before I go into that, I kind of need to roll back, because this is the ACCU conference. I'm not going to take it for granted that everybody here knows how DNS works or what it's doing or anything. So let's begin with DNS at the beginning. And this is the beginning of modern DNS, RFC 1034, 1035, Paul Mucker-Petris, November 1987. That was a long time ago, wasn't it? And that introduced the Internet Domain Name System as a consistent namespace for referring to resources, maintained in a distributed manner, and with local caching to improve performance. And it's a hierarchical, as I'm sure you all know, it's a hierarchical namespace. So you have a root at the top-level domains underneath the root, and domains disappearing down as you go. So looking at it another way, you have authority over what is in your database being distributed down the tree. Right at the top of the tree, we have the root of the tree. The chief authority of that is ICANN. ICANN, for those of you who don't know, is I don't really know quite how to describe it, actually. It's a quasi-autonomous international organization which, because it is a quasi-autonomous international organization, it is therefore political. And decisions get made there. Essentially, it used to all be run by the US government, but when the internet got to the point where the rest of the world said, hey, we've got a stake in this, the US government responsibilities were transferred over to ICANN. So it's ICANN that decides what top-level domains there will be. And some of you may have been aware that they introduced a whole bunch of new top-level domains a few years back, because the domain, commercially, the domain name system is, I like to think of it as basically a protection racket these days. Every time you open up new namespace, the reason you're doing that is to try and get people to buy it. And the reason these days you try and get people to buy it is to protect their brands. At least that's how it seems to me. Perhaps I'm a little cynical on the subject, but anyway. As it happens, the ICANN expansion of global top-level domains has possibly not been a rampaging success. People are giving the keys back. Mont Blanc, the pen manufacturers, they bought a TLD. And this is after you've spaffed, $500,000 on one of these. People are walking away from them because actually it doesn't really turn out to be much value in these. But anyway, and so we have a root, and underneath the root, we have the major top-level domains which we're all familiar, which are generally top-level domains or country TLDs, we call them. So here we've got .net, .edu, and .ca, because I nicked this drawing off a Canadian. And you'll see that, so ICANN's authority extends as far as pointing you at the next level, the authority for the next level down. You'll notice that you can. It's not a strict. It's not a strict tree in the sense that you can have cross-cutting delegations of authority. So, for example, verisign.ca, the Canadians will direct you to VeriSign's name server, which is also probably under .net. I mean, as it happens, VeriSign is the company that runs .net, but hey. So the root servers. If you're searching a tree, you've got to know where to start. And the root servers are the start at the top of the whole business. And that's a fixed list of IP4 and IP6 addresses, which is encoded into every device you own, pretty much. And there are 13 root servers. They're called a.rootservers.net through to m.rootservers.net. There are 13 of them for reasons I'll come to soon. And the root servers are operated by a variety of different organizations. ICANN themselves operate LRoot. And one of the things I do during my day job is run some monitoring and data collection off LRoot. The other interesting thing about the root servers is they're vastly different sizes depending on which organization is running them. Some of these are almost literally 2 PCs in somebody's office somewhere. Other ones, the ICANN one, and certainly a NetNod I know for sure is on a similar scale. The ICANN root server is about 300, 350 machines scattered all around the world, with appropriate routing magic to send you to your local one. NetNods is in a similar scale. I think RIPE is the European Internet Registry organization. I think theirs is on a similar scale. And certainly VeriSign's is as well. If any of you have been sitting there counting very quickly, you'll have discovered there's 12 of them. Okay. The reason for that is that VeriSign bought one of the other root server companies at some point or another. Anyway, in the world of DNS, we distinguish between different types of DNS server. And the most important one that we start with are what we call authoritative servers. Those are the ones that are the authority for a zone. Okay? They contain the data for that zone. Anybody who wants to find out about addresses in that zone or information in that zone, they must end up eventually at the authoritative server. And they're run by the zone owner. Okay? I should, as a matter of curiosity, at least, zones can actually contain multiple domain levels. The UK zone, the .uk and the .co.uk are the same zone. It just happens to be how Nominet run them. The ones that you tend to deal with most are recursive servers. These are the ones where you're asking them a question and they are going ferreting around the hierarchy to try and find the answer. Okay. So, if you are asking for ACCU.org and your recursive server has never heard of ACCU.org before, the first thing it'll do is go, well, actually, have I heard of .org before? No. Well, let's say I haven't. Right, go up to the root server and send a query asking the root server, do you know about .org? And the root server will say, well, as it happens, I do. it's over here. You then go over to the .org name servers and say, do you know about ACCU.org? And it will say, yes, I do. You need to go and look at this place, and so on down the hierarchy. And each piece of information that you get back has a TTL, a time to live, attached to it, which enables the recursive servers all the way down to cache them as appropriate, which stops the whole system sort of gunging up under a torrent of queries everywhere. Even so, the root servers can be busy. Funnily enough, about 95% of the queries you get on a root server are complete junk. I'm not really quite sure why, but there it is. The ICANN root server deals with something in the region of 10 billion queries every day. And I'm logging them all and sticking them into a database, which is probably another talk at some point. Anyway, now, the recursive server you deal with is typically run by your ISP. And you find out about it because when your computer connects to the network, DHCP tells you that's where you want to go to find out about, to do your name lookups. These days, of course, there are also public resolvers. Famously, Google 8.8.8.8. Does anybody use that? Yep. Quad 8, as we call it in the business. You may not know there is also Quad 9, which is a non-profit with partners, including, I think, Red Hat and IBM. There's Quad 1, which is Cloudflare. Now, that was great. I actually quite like that, because they knew that 1.1.1.1 was likely to cause trouble. They wanted it, and actually they had to go and negotiate for quite a long time with ATNIC, the Asia Pacific NIC, who were the people who actually allocated Quad 1. And they got it, but sundry people have historically used Quad 1 as an address that was never going to be assigned. Okay. And Cloudflare went ahead and said, Sodom will do it anyway. And so as a result, you can't use Cloudflare's Quad 1 on any Orange France domestic ADSL installation because they've been bad and they haven't read the docs and that sort of thing. But anyway. Sorry.
Could you just say possible language?
Oh, sorry, is this?
It just slightly sounds like jingling sometimes.
Oh, I better undo the clip. Oh, look, Mama, life in show business. Anyway, right. All right, recursive servers. And then finally, we have something called the Stub Resolver. And this is the thing that's running on your computer and is reading, well, if you're a Unix head, it's reading your etc resolve.conf or whatever, and handling the name resolution on your system, which it's typically doing by talking to the recursive server that you have been given, or which you have chosen, or which you've chosen to use. Right, so that's the sort of overview of how the whole thing conceptually hangs together. What's actually going on the wire? Because we're programmers, we like to know this kind of thing. The format of a DNS message is a sort of good old-fashioned 30-plus-year-old binary format, which is this. The format of both a query and a reply is the same. And you distinguish them by that bit there. If it's a 0, it's a query, and if it's a 1, it's a reply. Every query has an ID in it. And the ID in the response must match the ID of the query. Okay? So you can basically have lots of queries in flight at once, and you can match them all up when they come back. There's an opcode which for our purposes, we can probably say just usually has one value in, which is this is a query. There are various and sundry flags. And the flags are doing things like indicating, well, AA indicates in a response whether this was an authoritative response. This came from the horse's mouth. Okay. TC indicates that the response is truncated for some reason. RD and RA are recursion accepted or recursion desired. So you can send a query saying, look, I don't want you to recurse. Just tell me whether you know about this or not, for example. The important things, apart from the flags, an R code, a response code, which is usually going, yeah, you made it, or NX domain. No such domain exists. Well, there's a variety of serve fail is the other favorite, which means that, no, I just give up. Anyway. And the rest of the message is 4 distinct sections. Questions, answers, authorities, and additional. Now, the question is what the question is. So a query will only have a question section. And when you get back a response, the response includes the question you've asked, but also includes answers, this is what you wanted, authority, which is this is the details of who's giving you these answers, and additional, which contains information that you may need to know to proceed further. For example, if you're being sent off to, if the reply you're getting is saying, I don't know the answer to this question, you need to go and look at this, the authoritative server for this subdomain over here, then the additional data will typically include the IP address of that server that you need to go and look at. Now, there are some issues there in that, generally speaking, you should only believe it if that IP address, or sorry, if the subdomain server is part of the same authority section, because otherwise they could be sending you to God knows where. But anyway, and then at the top here, there's just counts of how many records you have in each one of these. I don't really intend to sort of try and tell you everything you need to know about all this. I just want to give you a sort of flavor for how the whole thing works. So inside a question section, we have the queue name, which is the name you're looking for. It's actually given not as a string with stops in it, but a series of labels. A label is a count of characters followed by that number of characters. And you proceed down those until you hit something with a length of 0. Whatever, doesn't make much difference. The queue type is the query type. It's what the information that you're looking for is about, and I'll come on to that in a moment. And finally, there's something called a query class. Essentially, pretty much anything you send these days has a query class of internet. There are some engaging old bits of 1980s network tech which have assigned constants, and there is one actually that's used occasionally. There's a class called chaos, which was some kind of networking protocol at some point. And there's a well-known hack for inquiring what the version of the name server you're talking to is by putting a queue name of version.bind in it and querying that with a class of chaos. But anyway, the sort of little grubby sections you get in any 30-year-old protocol. Responses are a little bit more complicated. A name, a type, and a class exactly as before. The TTL, how many seconds you should carry on repeating this information to everybody else for. Okay. A length, and then just a slab of data of that length. And it's the data in there that holds the addresses or other information that you're getting back. I mentioned the query type. There's quite a lot of query types, most of them only these days of historical interest. These are the typical ones you're sending. Okay. A, to ask for a IP4 address. Quad A, to ask for a IP6 address. I'm sure most of you recognize at least some of these. Text is just asking for general textual information, which you can find all sorts of stuff in that. But anyway, so how is this sent to and from you to the resolver and from the resolvers up to the next level? Well, everybody knows the answer to that. DNS uses UDP, except when it uses TCP. Because from the word go, DNS has had an option to fall back to TCP. And the reason for this is if you have a large response, you may not be able to fit it into a UDP packet. This is the reason that there are 13 root servers. And indeed, if you ask for the list of servers for .com, you'll get 13 answers. Because that's the size of a response that you can pretty much guarantee is going to fit into a 512-byte UDP package. Now, historically, TCP was not a path that was actually traveled very much. And server TCP code was not hugely cared for. There was a point, and it was a surprisingly recent time ago, where you could do an effective denial of service attack on a lot of the major name server softwares just by opening half a dozen TCP connections to them and sitting there. Because they had a fixed pool, they didn't try and time out anyone's connection or reuse connections or anything like that. But things have changed a bit. Sorry? Not quite, but yeah, you're close. Some of you may have come across the recent DNS Flag Day. DNS Flag Day was related to this beast. You'll see this is Paul Vix's brainchild from 1999. It's an extension mechanism for DNS. We've hit this point where we kind of need more flags. We'd really like some more return codes. We need some way of extending the protocol a bit. EDNS 0, I beg your pardon, is a rather engaging hack, which I'll come to in a moment. Its great saving grace is that it allows you to increase the size, to report a much bigger size of UDP messages that you can accept, so that the other end knows that it's not limited to 512 bytes or whatever. And that became quite pressing for reasons relating to both IPv6, because IP6 addresses are rather bigger than IP4 addresses. All the crud that people started putting in text records. And DNSSEC. I'm going to come on to DNSSEC just in a little while, just to give you an overview of what that's all about. The way that EDNS 0 works is it allocates a particular query type called opt, number 41, which is never sent on the wire. It only appears as, hang on, have I got that right? I think so. Anyway, you can only have one of them. It has to go in a particular section. And it repurposes the fields that we've talked about, or I've talked about already. It repurposes them to mean something else, basically. Okay, and more importantly, it uses the section data to provide a means of adding sundry options, sort of semi-indefinitely extensible. There aren't actually too many defined at the moment, so I'm going to come on to one of them shortly, which is this one. This is a quite unusual RFC, Client Subnet in DNS Queries. This is very, there aren't many RFCs where the text of the RFC actually tells you not to do this. What's going on here is you have a resolver. You're talking to a resolver of some sort. It is sending your queries that it can't answer further up the chain. Okay. When they go further up the chain, of course, the communication appears to come from the resolver you're talking to, not from you. It doesn't have your IP address on it anymore. However, CDNs, content distribution networks, and particularly Akamai, kind of like poster child for this, they're often reporting content which is kind of localized to where you are. And unless they know some kind of indication as to where you are, you may not necessarily get the right content back. So what was happening were people were putting unofficial hacks in to provide it's typically the subnet, not your individual address, to the further up servers so they could deliver a content appropriate to your geographical location. And in the end, the IETF decided they had to standardize this, but they don't really like it because from a privacy point of view, it's a loss. All of a sudden, people further up the train know where this query originated from. And I'm coming on a bit more. In fact, a lot of the rest of this talk is going to be about those kinds of privacy issues. Okay. The final thing I'm going to give you a quick overview of here before we go into specific new protocol stuff is DNSSEC. Now, DNSSEC had a long and unhappy gestation. This is DNSSEC as we use it today, March 2005. It ended up pretty much being the second attempt after they'd spent 10 years on the first attempt and discovered it didn't scale, which is always a problem. DNSSEC is about assuring the authenticity of DNS data. Because remember, this stuff is all flying about in clear. And as the internet moved from the internet of the late 80s, which was good guys talking to good guys, to the internet of 2000s plus, where there is all kinds of nasty stuff going on, it can become important, or at very least useful, to know whether the data you're getting back is actually what the authoritative server meant you to get. So DNSSEC is all about cryptographically signing the data you get back so you can check it and verify that, yes, this really is what the domain owner intended. Like IP6, it's one of those systems where the rollout is glacial at best. I think I've got a slide about that in a moment. Essentially what's going on is right up at the top of the tree, there is a root key, which is published. Okay? For sundry operational reasons, the way this works is at each level in the hierarchy, you have a key signing key and then a zone signing key. The key signing key is changed infrequently. The zone signing key, which is signed by the key signing key, is rotated much more frequently. Okay. It's the zone signing key that is used to generate additional DNS records with cryptographic signatures of the data you're being reported. So that you can then verify that, because of course what you see of these keys are the public key. So you can verify that the information you're receiving was encrypted by the people who said it, who should, the people who originated this. This DS record here is a signature link. So it's containing a signature of the key signing key for the next layer down. That is the link that means that you can't inject CRUD into things as you go down. So at the end of the day, you come down to a final. This is just showing you what the final layer looks like, and you can verify that the address that you got back really was what the domain owner intends it to be. To do this, they introduced a few new record types. This is the brief summary of those record types. A record type for a key, record type for a signature. Name existence has been a bit of a tricky one. You see, because as well as verifying that this name was indeed what the authority intended, you also have to have a proof of negation. If you get NX domain, was that really because it doesn't exist? NSEC was the first attempt at doing this, which basically, but the way it worked was essentially to tell you the name before and after in order the name you might be looking for. People then got upset because that actually allowed you to enumerate an entire zone. And some people don't mind that because their zones are public. Some people do. They don't want you enumerating their zone. NSEC 3 was an attempt to, there was probably an NSEC 1 and 2, I don't know. NSEC 3 is an attempt to do the same thing but do it all through hashes. So you can't enumerate a zone. I'm not quite sure where we're up to at the moment. I have a hideous feeling that someone's found a theoretical way around that, and there's an NSEC 5 in preparation. But anyway. So where we are at the moment with DNSSEC is, hang on. The route has been signed for quite some time. And back in January, February, there was a major event. ICANN rolled the root key for the first time. And as you can imagine, the amount of sweat that went on before they did that was huge. And one of the big things about that is that as well as rolling the key, they increased the key size. Previously, it had been only 102 bits. It's now 2K. Unfortunately, when you get to .uk, the zone signing key is still only 1K. I'll come on to a bit more about that in a moment, because it has an implication for whether people actually start relying on this crypto or not. Anyway. DNSSEC carries a few more bolt-ons to what's on the wire. There's a eDNS Flag DO, which just tells you, well, on the query, it tells you whether the client understands DNSSEC or not. And there's a couple of new main flags just telling you whether, first of all, the data was authenticated or not in a reply to you, and otherwise, whether the client would like to receive only authenticated data or whether they're happy with unauthenticated data. If the client does not set the CD, the checking disabled flag, if they make a query and there is an answer for it, but the signature doesn't match, you get an X domain, I think. Which leads us on to another little problem. How can you actually use this? So I beg your pardon, serve fail if authentication fails. How do you actually use this? So you need a resolver that's doing it. You need the chain. Well, if you're sitting there with an ordinary computer, you're probably relying on your resolver to do all this stuff. So your ISPs or wherever it's a thing. Quad 8, I think all the public resolvers do DNSSEC now. But there's this last mile problem. You're talking to a resolver. How do you know things haven't been tampered with between you and the resolver? If you're really lucky, your Stub Resolver can validate. It probably can't. I mean, can your resolving server validate anyway? Another question. And as I said, even if your resolving server can validate, can you trust the link between you and the resolving server? You can always do local validation. Okay. One of the issues that's kind of bedeviled DNS has been that most system resolvers got to the point where they worked and they've kind of stopped. The resolver inside glibc does not have DNSSEC support at the moment. There's been much talk about it, I believe, but I still don't think they've actually got it. This, incidentally, is one of the drivers for the Linux people amongst here. One of the reasons that systemd includes its own resolver is the systemd resolver does do DNSSEC. Anyway. And one of the things I think is quite interesting about DNSSEC is you can, if you're set up with everything signed, you can use it as an alternative public key infrastructure. Rather than relying on a host of, how many certificate authorities are there these days?
150-ish.
Yeah. Rather than relying on all of those, you can stick your key, your certificate into your DNS, and you can, provided you trust ICANN not to have leaked the root key, you can then be assured that this certificate is your certificate. Now, there is, if you're really interested in this, you can go and find out the details of what ICANN do when they roll the root key. Okay, the root key is kept in a safe. I'm not sure, it's not inside a mountain somewhere, on tamper-proof hardware. They're only allowed to open the safe. It's multiple. You need multiple people who all have different bits of the combination. Every time they access this, there's a ceremony protocol. It's videoed. They have representatives of the great and the good from wherever and stuff. I particularly like. We tend to clump all these together under the title of DANE. DNS authentication of named entities. You can set up your SSH server, for example, so that it will look up the certificate and it knows. It doesn't ask you that sort of, is this your certificate? You know the question that everyone answers yes to all the time. It circumvents that. So anyway, this is where the world was, 8, 9 years ago now? And then this happened. Who's he? Snowden, Edward Snowden. And it turned out that the world's security agencies were monitoring the internet to an extent way beyond what anybody had ever really considered at this point. And this disturbed an equilibrium inside the IETF, because the IETF previously had essentially kept out of interception issues. They'd refused to modify protocols to make them easier to intercept, but they hadn't really pushed in the opposite direction. Snowden comes out, and people start writing papers. And before you know it, there's RFC 7285, which is now BCP something. Pervasive monitoring is an attack. Where the IETF basically says we consider any kind of pervasive monitoring an attack, and all future protocol work should try and mitigate the possibilities of these attacks as far as possible. They also, in the DNS world, they also set up a working group, DNS privacy, with the goals specifically of encrypting the Stub Resolver DNS link. And the thing is, once you've done that, you can do exactly the same thing up to an authority. They actually stuck at that and just said, well, the group can also think about doing it upstream. Dprive sat and thought about this for a while, produced RFC 7626, which is a quite interesting reading list of the privacy considerations of relating to the DNS system. What exactly are you exposing? What can people do with it? How can they get hold of it? And so forth. It's quite a fun document, written by a terribly genial Frenchman called Stéphane Botsman. But anyway, and in 2016, they produced a couple of new RFCs, the first one of which was DNS over TCP. Now, as I've said, DNS over TCP has been a thing since day one. This RFC is essentially updated recommendations for how you should operate this and how it should work and how it should scale. And once that was solidly in place, we moved to RFC 7858, DNS over TLS. It's doing the obvious thing. If you have DNS working over TCP, well, why don't we just run it over TLS instead? And these days, this is the front page of that RFC. These days, actually, since DNS over HTTP came out and called itself DO, we're now backforming DOT for DNS over TLS. Okay, so it's exactly like doing it over TCP, but it goes to port 853. DNS goes to port 53 for UDP and TCP. DNS over TLS goes to port 853. And it has a couple of, the RFC specifies a couple of different operating modes. The first one of which is opportunistic. So your DHCP server tells you, right, here we go, look here for your DNS resolver. Opportunistic mode then says, okay, well, I'll try connecting to that address on port 853, see if I get anywhere. If I do get a connection, then I'll look at the certificate and see if I can validate that. If I can't, I'll use it anyway. on the grounds that it would at least mean that your traffic is protected, even though there might be a hole at the other end. It's basically trying to do the best it can in the circumstances. There is should we say, a somewhat open question here about how you report to the user what's going on. The RFC, for obvious reasons, doesn't specify that. Okay. But it tries to do its best, and if it does manage to get a TLS connection of whatever sort, at least it'll defeat passive surveillance. Someone just sitting there collecting all your traffic. There is also strict mode. Now, with strict mode, you specify on your system a key fingerprint for the server you're wanting to use. And everything gets checked at that point, and it will only carry on if the fingerprint matches the keys. So you can be 100% sure that the server you're talking to really is the one that you think it is. Now, notice that this is complementary to DNSSEC. They're doing different things. DNS over TLS is about protecting your data as it's communicating. DNSSEC is about authenticating that the data you got really was the right answer. And they're two different things. Okay, I often find sort of a lot of people think, oh, if I'm running it over TLS, then it's secure. Well, yeah, it's secure in one sense, but it's not secure in the, yeah, you can be sure that what you get is what the server sent. What you can't be sure of is what the server sent was what reality is. Anyway, moving on. So yeah, either way, adding at least integrity or transport has benefits. It's worth doing. And since this particular protocol is a trivial upgrade, it's exactly what any of us as a programmer in the room would have said. Oh, I know, let's just do that over whatever. It's simple, it's straightforward. And it's now quite widely supported. In particular, I will mention that Android Pie, you can go and turn this on. In fact, I'm not sure it doesn't do it by default. We still need native support for Windows, macOS, and iOS, unfortunately. As I said earlier, there's a bit of a problem with getting people to, they often say, well, name lookup works. Why should we do it? It's worked fine for 20 years. Why should we do anything else? So it's just not really a priority. I mentioned already Stubby. I'll mention Stubby again, but that's mostly because we work on it. There's a library called GetDNS, which it's a C library, and if you want to do client DNS, it's probably the best option there is at the moment. It's written by, well, the heads of the project are NL NetLabs, which is basically the research division of the people who run .nl, who are big cheeses in the DNS world. There's only typically, apart from custom jobs, and most of the world's DNS runs on one of 4 different servers. Okay, nearly everyone's heard of Bind. Okay, if you're running serious traffic, and you probably want to have a look at Unbound, which is NL NetLabs' recursive server. And there are some Linux distributions these days that actually install a local Unbound on your system. Because, of course, Unbound can also do DNSSEC and so forth. Or not. Not is done by CZNIC, the Czech domain people, who are also a group of really cool people. DNSDist is a load balancer thing. It's done by, if I'm right, it's done by Power DNS. Power DNS is a open source but commercial organization. The founder of which is Dutch as well. Yeah. Yeah, there's some kind of Netherlands mafia thing going on here. But anyway. Stubby, going back to Stubby, Stubby is an application that uses GetDNS and acts as a local resolver. You run it on your system. You set your resolver to be 127.0.0.1, and Stubby takes care of the upstream stuff. And I can talk quite a lot more about Stubby and why I want to change how it gets built on Windows and that sort of thing. The short answer which is NLNet Labs is a somewhat conservative organization who doesn't see any reason why AutoConf shouldn't be used for everything, though not AutoMake. To give you an idea of where they're coming from, until they revamped it late last year, their previous website was put together using M4. I don't know if you remember M4, anyone? And not only was it put together with M4, they advertised it because they were really proud of that. Anyway. Dot is there. Sorry, yes, hi.
For what it's worth, Android 5, the setting is called private DNS.
Right, thank you.
Turn it on, automatic for
Cool.
specific host names.
Cool, thank you. Sorry, my phone's far too old. So dot exists, and dot is a thing, and we like it. I like it, anyway. Another little bit of work that's been going on is something called QName from privacy perspective, is something called QName minimization. And this applies, this again is a measure which is irrelevant to your transport, but may improve your privacy a bit when widely deployed. What's going on here is when your query goes up to the root server at the moment, the root server gets the entire query. Makes very interesting reading sometimes, I can tell you. Anyway. But of course, the root server doesn't need your entire query. It just needs to know what the bit it needs to answer is. QName minimization is about doing that. It was actually done by the DNS Ops group rather than a different working group, the main DNS working group within IETF rather than dprive, but that's politics. And it's an attempt to minimize, shall we say, the information leakage that your query is causing as it goes up the chain. DNS being DNS, of course, it broke things. It really only breaks things, I believe, when people are doing things they shouldn't have been doing anyway. Okay. However, it's a fixed rule. Certainly, it's a fixed rule in the DNS world that it doesn't matter how stupid something is, somebody somewhere in the world is doing it. Okay. Anyway. And at this point, I'm going to have a little diversion because I've been talking about all this stuff that's been shoveled onto DNS over the years. It's a 30-year-old protocol. And we now have this problem that there's the original RFCs and there's all these incremental RFCs in between time. And actually, the amount that you have to read before you really get a view of how the modern DNS works is a little bit alarming. And you also need someone around to tell you which are the ones that are still valid and which are the ones that are now sort of historical curiosities. And last year, at the IETF meeting in London, Bert Hubert, who is the founder of Power DNS, introduced something he called the DNS Camel, which is simply which at the time was simply a statement that this stuff is getting out of control. There are now, you have to read about 2,500 pages of RFC, and more to the point, you have to know which pages to read. And it's about time we tried to reduce the overhead of this, or at least make it clearer where you should read. I think that people have talked in the past about attempting to redo the documentation, but it's a huge job, and no one's got time for it. But Bert, bless him, has a couple of interesting little projects going. The first, I mentioned first this site, powerdns.org, DNS-Camel. That is just a summary of what RFCs are currently active and what ones you should probably read and how many pages there are. It's the first thing you need to start. The second one is more fun. Hello DNS. It's a community attempt to try and document what really goes on. What are the silly little mistakes that you can make if you try and implement, say, a DNS resolver? Don't try and implement a DNS resolver, by the way, but should you try to do so, what silly little mistakes you may make because you're just reading the RFCs. There was a bit of a howler in the first version of the systemd resolver because they weren't, if I remember this rightly, they weren't randomizing client port numbers. You see, you remember back in one of the early slides, I said there's a 16-bit ID for each query, which is used to match the reply. There are and have been a variety of attacks on DNS which revolve around sending a flood of replies back to a questioner with bogus data in them, and just hoping you hit the right query, the right query ID. Basically, 16 bits of entropy is not enough these days. And so one thing that's been done is one thing clients typically do is randomize the source port they use for sending the query to add more entropy on that way, because you have to get the right port back as well. Some early implementations would even go, right, okay, well, my first query I'll call 1, second query I'll call 2, sort of thing. I believe there are even instances of adding additional entropy by mucking with the case of the query name. But I haven't seen that much myself. Hello DNS is a wiki, but it's also some software projects. If you want to see what a simple resolver looks like, written in C++, because Bert is a big C++ fan, who has been valiantly trying to convince the rest of the DNS world, certainly, that C++ is actually these days a really good language for writing things in, and not, as they have assumed, a way of producing really complicated and totally runtime inefficient code. Never mind. However, so if you really want to go and have a digger on this, Hello DNS is a great place to start. They're not coping with all the edge cases, but there are example servers and example resolvers on there. So, back to Do. I don't know if you remember the previous timeline. From the formation of the dprive working group, I think it took at least 2.5 years to get to a point where dot became a thing. Do was a bit quicker. It was first discussed in March 1917. A first draft was published in May 2017. A working group was formed because it was halfway between the HTTP people and the browser and the DNS people. So they set up a separate working group to condone it in September 17, with a mission of standardizing encoding for DNS queries and responses suitable for use in HTTPS. The published draft was adopted in October 17. Submission to the IESG is when a working group says, right, we're done with this, we think this is the way to go, it goes up for high-level peer review. That submission to the IESG yeah, I do beg your pardon, that's July 2018. Goes to the IESG in July 2018, is approved in August 2018, and published in October 2018. The time lag between approval and publish is waiting for the RFC editors to work their magic and dot the I's and cross the T's, and so forth. This is ludicrously fast by IETF standards. So what happens in DNS over HTTPS? Well, each DNS query response is an HTTP exchange. The RFC says you must use HTTPS. And in fact, you want to use HTTP2, because if you don't, your performance is going to be abysmal. Okay. Because you're using an HTTP exchange, HTTP is taking care of matching the response up with the client. So you should just put an ID of 0 into each query, because you're not using that ID field anymore. There is no equivalent of the opportunistic and strict modes described in the RFC at the moment. It says it must be configured externally using a URI template. So basically something that looks like this, where if you're doing a GET, I think, that DNS is substituted with the GET query. So let's have a look at this on the wire. Sorry, I beg your pardon. Yeah, that's right. It defines a HTTP media type of application/DNS message, which is exactly the same as a DNS UDP packet. It's slightly different from what goes over the wire in TCP, because when you send DNS data over TCP, you send a UDP, the same data that's in a UDP packet, but prefixed by 2 length bytes. Because, of course, TCP, you don't know where your chunk of data ends, so you must indicate that. HTTP, yeah, so it's exactly the same as a payload of a DNS packet. There's a maximum size of 64K for the packet size. In fact, there is other DNS RFCs now define 64K as being the maximum size of a DNS packet, whether it's in TCP or whatever. So the door's open to future definitions of alternate media types. Because remember, the browser crew have got their hands on this. What's the first thing they're going to want? DNS queries in JSON. And I expect that to be hurtling down the rail line very soon now. People have actually sort of written drafts for representing DNS in JSON in the past, but it's not really been considered, as far as I know, for over-the-wire things. The other big difference with HTTP is, of course, HTTP has got its own cache control. So you have to make the DNS TTLs and the HTTP cache control coincide. And the RFC contains rules for doing this, and reminders that, for example, if you're getting a response from an HTTP server with a DNS TTL in it, the response from the HTTP server will include the age, how long that's been in the HTTP cache, and you need to subtract that from your TTL before you get the correct DNS TTL. So let's see it in action. And this is an HTTP GET query, where you can see that DNS equals has been substituted with this little lot. And that is just a UDP packet encoded in base64 URL. You can do the same thing through POST. And in that case, yep, that is just a bog standard UDP DNS packet. So like DOT, it's actually quite easy to implement. DOT, if your DNS server does not support DOT, it's trivial to have it support DOT just by bunging HA proxy or Nginx or something in front. Things are a bit more difficult for DO, but it's still the sort of thing that you can whip up a proxy for in a very short period of time. And here's a response coming back. You'll notice the cache control maximum ages, whatever. If we were to unscramble this, we discover it's a response, it's this response. And if you look, you can see bits of that in there somewhere. Where's DB8 gone? I could have sworn I saw it earlier, but DB8, there we go, maybe. Yeah. So, on the face of it, actually, this isn't very different from DOT. This is just another transport mechanism for sending DNS queries. Why would this be a problem? No, there's not really a problem, is there? Which raises the question, well, why do you want this? And some of the reasons for that are because we're browser people. There are useful things you can do in a browser with this. In particular, I'm probably coming up to that later. If you're sending a page down, if you can, you could also send the requisite DNS to preload the caches of the receiver so that references from the page you've sent them, they don't have to do a lookup on, provided they trust you, of course. Anyway, having said it's equivalent to DOT, of course, it's going over HTTP, and so there are potential privacy questions here because of all the stuff that HTTP adds. The RFC itself doesn't say anything about stripping out HTTP headers like user agent or whatever, though I expect that's what will probably happen. But in some respects, I feel this is a sign that this perhaps hasn't been thought through as far as it might. There are potential new privacy concerns because of HTTP. So, connections, how are we going to do this? Is DOE going to be something where a DOE server is dedicated to DNS traffic? Or are you just going to mix it in with the rest of HTTP traffic to somewhere? And this is basically where the fun starts. Because if you mix it in with other HTTP traffic, you can argue you get increased privacy. Because people won't know what's a DNS lookup and what isn't. It also becomes impossible to block. And that's the big differentiator with DOT. DOT, remember, is going over port 853. You don't know what it is, but you know it's DNS traffic. Now, where are we with support for all this? Well, the answer is there are implementations around. Cloudflare are supporting it. Google have got experimental support in there, and they will be doing this. And Quad9 have got support with actually sort of 3 different layers of service in it. So the public resolvers are moving to allow you to do this. And there's various other, everything else is, there's bits of support here, there, and whatever. This is very early days. Remember, this RFC came out in October last year. Okay? Client status. There are already support for this in browsers. In Firefox, there is support in Chrome. It's in the code, it's not turned on. Curl has support. There's an Android app and various other more experimental bits of support. GetDNS, since I mentioned GetDNS previously, GetDNS, we have a branch on which it's supported at the moment, but there's a bit of a way to go before that will be sufficient quality to make it into a release, because it's changing a lot of the mechanism of how lookups take place, for the better, nonetheless. And it's starting to go into, direct support is starting to go into servers. It's in there's an experimental version of DNS dist around, and there's a branch for NOT. It's not in the main line of NOT, but it's coming. Going back to browsers, because this is the interesting bit. The browser people also say, as I've mentioned already, operating systems are slow to support new DNS features. Perfectly true. Can't argue with that. We care about the privacy of our users. And there's the possibility of reduced latency in the browsers. Yeah, this is all probably true. And Mozilla have gone as far as to make some statements on why they want to go with DO, not DOT. Which is essentially, it's cool, I think. But anyway, however, Moziflare. Mozilla did an experiment last year. Mozilla would like to turn on DO for all their users. With Cloudflare, as they've invented this new term, trusted recursive resolver. Cloudflare is their nominated trusted recursive resolver. We have a resolver we can trust to protect our users' privacy. This means Firefox can ignore the resolver the network provides and just go straight to Cloudflare. Oh yeah. We won't check for DO or DOT on the local resolver. There's an interesting thing here in that discovery of a DO server is something that's still under discussion. There is a draft on how to do it by doing an insecure DNS lookup, which I can't quite see the point of myself. However, the important thing here is Google and Microsoft have both said that what they will do is pretty much what DOT does, i.e., you'll get a redress of your resolver off your network operator, and they will then go and probe for DO at that address. And actually, I think that's going to be what happens. In an ideal world, you probably just have a different DHCP type. Unfortunately, I think that's probably not going to happen officially, because, oh, my DHCP is insecure, man. We need to be reducing the amount of data we send through DHCP, not increasing it. I'm not really sure that that is totally a valid argument myself. But anyway, I expect de facto that what will happen is that, yes, people will do what DOT does and probe at the existing address. The problem we're attempting to solve here, and this is Mozilla, by the way. The problem we're attempting to solve here is an attack on the user's name resolution from an attacker with full or partial control of the network. Okay, this is from a post to the one of the relevant IETF mailing lists a couple of weeks ago. Okay, think about that for a moment. Mozilla have just declared that your network is the enemy. That may be true for some people. The user will be informed that we have enabled use of a TRR and have the opportunity to turn it off at that time, but will not be required to opt in to get DO with a TRR. Oh ho. Now, I expect you're all familiar with the 7-layer OSI model, which I can only remember because there was a great book in the mid-1980s by a fellow called Joel Padlipski about computer networking. And his acronym to help you remember the layers was all protocols should talk nicely like Padlipski. If you go to an IETF conference, you'll see people wandering around with the 7-layer model on their T-shirt and an 8th layer labeled political saying, "You are here." Okay. In fact, I've discovered that there is a semi-official This is Layer 8 individual, Layer 9 organization, Layer 10 government. This is blessed by Bruce Schneier, no less, so we have to take it seriously. I also discovered while I was researching this that there's an RFC from 1998, one of those RFCs that gets published on the 1st of April, which adds additional layers for the 4-layer TCP model. It defines a layer 5 political and a layer 6 religious. We're firmly in this territory at that point. And I've found this quite a useful framework for discussing some of the implications of this. I had a whole load of points I wanted to make about this, but was finding it very difficult to arrange these into some sort of coherent order. So I'm going with the top 3 levels of the model. And I'll start at the individual layer because as they've said, Mozilla are going to be going for the end user on this one. And what they seem to be talking about at the moment is presenting you with a little box which just says, we've made your DNS more secure. Do you like this or would you like to back out? Now, what's the implications of this going to be? And the big one, of course, is the sudden split between your system resolver and what's happening in the browser. If you happen to use one of those home routers that I think particularly BT do, where they give names, where the router itself, your home router, does some names for you, it generates names like system name .home when you connect to the router. Okay, that's going to stop working. Suppose you use a VPN. Now, VPNs often, when you connect with a VPN, it often changes the resolver to the one that the organization you're connecting to is using. So if you are VPNing into your corporate network, you can then see all your corporate network names. That's going to break. Are we looking at a world where we're going to have to configure DNS for every individual application? I don't know. If you sign up to an ISP these days, some of you may have seen TV commercials where ISPs talk about their parental control service. You know, sign up with us and we will guarantee that your kiddies don't see anything that might disturb them. That typically works by blocking certain DNS lookups at the ISP level. You sign up for, you click the box on Firefox and all that will suddenly stop working. And you may not well realize this at the time. There's a whole issue of informed consent here, and it's a problem. Because actually what we're talking about is quite technical stuff. I went to a talk a little while ago where the speaker was struggling to come up with a term for basically the non-tech initiated, or whatever, and eventually resorted to muggles. Okay. Which I think is great. How the hell are muggles going to give informed consent for this sort of thing? And what is the best choice for a user? And the answer to that depends. What is your context? There's an awful lot of talk about, when this is being discussed, there's an awful lot of talk about this makes life safer for dissidents in Syria. Although personally I tend to suspect any Syrian dissident relying on just this is going to have other problems and much larger ones very quickly. However, as it happens, my mum and dad both use Firefox. And for historical reasons, they have TalkTalk as their ISP. Now, one argument is that TalkTalk is based in the same legal jurisdiction as they are. TalkTalk is subject to GDPR. You know what the regulatory framework is. Cloudflare is a US corporation. What are they doing with your data? Well, Mozilla have a strict privacy agreement with Cloudflare, what they're allowed to do, you can go and read it. But nonetheless, if you have any beef with them, you're going to have to go somewhere else entirely. You're going to have to cope with an unfamiliar overseas legal system. On the other hand, of course, TalkTalk have amply demonstrated that they're not very good at looking after your data. So maybe, although Cloudflare are not entirely spotless, Cloudflare are not nearly as clueless as TalkTalk. Now, my point here is, if this goes ahead and Firefox pops up a little box, I know what's going to happen. Dad's just going to push whatever button he can to make the whole thing carry on working. Okay. Mummy's going to ring me up and say, what do I do? What does this mean? You know, Firefox are what? They're going to show you a dialog box about that big. Any kind of meaningful answer to that question is going to involve a half-hour discussion. I don't think it's something that you can just put in. It's a bigger problem. This isn't just DOS specific, in that this also applies to the use of public resolvers like Quad 8 and Quad 9 and so forth. But as far as I know, this is the first attempt to use them by default. Let's move up a layer. Many organizations operate what's called in the trade split horizon DNS. That means that when you are inside an organization's network, you see a whole bunch of host names that you do not see when you're outside the organization's network. If your browser has suddenly taken on itself to use a non-organizational resolver, that might give you a few support problems, at the very least. ISPs often operate local content caches. If you're a big ISP in the UK, you probably have some enormous fat pipe to the Beeb and a lot of iPlayer content or whatever on your network already. And when people are trying to access this, they're getting it straight off your network rather than having to go through the interconnect to the Beeb. It's going to break that, or potentially may break that. If you're answering support calls, are you going to have to worry about which DNS they're getting their answer from? And fundamentally, it seems to me that if you're within an organization, organizations don't generally tend to regard their own networks as an attacker. Okay. The employees using their networks, or whatever, they don't think of them as people who need to be protected from the organization. There's a bit of a philosophical disconnect going on here. Sarah has been given her version of this talk, which is much more aimed at network operators at places like RIPE and the UK Network Operators Forum. And the reaction has been something along the lines of, they're doing what? And I'm blocking it, I'm banning it. It depends on how you see a network in many ways. Paul Vixie, one of the grand old names of DNS. My network, my rules. Which I find it kind of hard to argue against, actually. There is an argument, if we're talking about an ISP here, and you don't have a choice of ISP, then things change a bit. Now, in the UK, we're lucky in that we have a wide choice of ISPs. We can always go somewhere else. We can always go to another ISP whose privacy terms we like a bit more. We can go to an ISP that does not monetize aggregates of their DNS traffic. Some ISPs do that, okay, particularly in the States. And it's very common, I think, for technical US people to see their ISP as the enemy. And I think this is driving a lot of this. That's my feeling about what's going on. At the governmental layer, and some of this stuff, oh, sorry, hi.
Just a small question, because the main point of discussion seems to be that we have DNS,
Yeah.
which is across the entire internet, and everybody sees the same things.
Yeah.
Versus what's essentially an attacker modifying that local view.
Yes, yeah.
If you have a local network, shouldn't you just try to make it part of the global network, or try to do something that's local, like MDNS?
Yes.
Like you
Well,
stop messing around with the global DNS and pretending that it's yours to modify.
well, yeah. Yeah, I see what you mean. The thing there is that there are now these uses of the global DNS. A lot of this is not so much about whether people ought to be doing this or whether this is the best technical way of achieving a particular goal. It's what's happening at the moment. I'm just coming on to some of these other things as well. If you're in the UK, UK government regulations force ISPs to block access to particular websites. ISPs typically do this through DNS because it's cheap and it works well. The other things they have in their toolbox are firewalling or mucking about with BGP. And that tends to be a much bigger hammer, I put it that way. Here's another big one, malware detection and mitigation. An awful lot of malware these days uses DNS as its command and control system. Okay, they started off by just saying, we'll use this particular site. That's easy. They've now moved to algorithmically generating domain names. So the malware can sit there and cycle through 20,000 of the damn things, and you just need to register one of them to control your malware with a text record. Something. And detecting and blocking these is something that certainly large network operators, and indeed in the UK, the National Cybersecurity Centre, spend a chunk of their time doing. In other words, there are valid reasons sometimes why organizations need some visibility on what's going on their networks. I talked to one guy who used to operate the .ca domain, and he was saying that, you know, at some point, he doesn't mind if the DNS traffic's encrypted. As long as he can tell it's DNS, because if it's malware, it typically has some sort of very strange access pattern. You can detect it and you can block the endpoint without actually knowing what's actually in the channel. The problem comes if you can't interdict it. Now, so far, Cloudflare and everyone have said we will only be doing DoH on dedicated DoH addresses. The danger here is if suddenly if suddenly it becomes available, say, on Google, because you can't block Google. Okay, and you know, I've had people say to me, if that happens, I'm sorry, I am just going to have to force everyone to use a proxy on my network so I can man in the middle everything. And I don't want to do that because it's a pain in the arse. I don't want to see your data, and it's extraordinarily expensive. Anyway, which takes us finally up to the, shall we say, the religious or philosophical level. Is DNS going to go the way of email? Who here operates their own email server? Okay, who's using Gmail or Yahoo or whatever? Email used to be something where every ISP had their own email server. And now most of the world's email is in the hands of maybe 10 organizations. Is DNS going to go the same way? Are we moving slowly towards an internet which is just controlled by a few big corporations? And indeed, is the logic of pervasive monitoring being an attack that we have to go all the way to an internet where every single protocol is on HTTP to port 443, so you can't tell it from anything else. I don't know. This innocent little transport upgrade has suddenly unleashed all these questions. And they're being which the IETF is vaguely trying to grapple with at the moment. They've actually, a couple of days ago, they set up a new dedicated mailing list to try and shift all the traffic off the other ones. You know, I was 100 messages behind practically before I started. And the most sensible comment I've seen so far on there was somebody saying, because there's been a lot of discussion, as you can imagine, about GDPR and opt-in and so forth. The most sensible comment has been, look, this is a legal issue. The law is a technical specialization of its own right. This, for us to be talking about GDPR, makes about as much sense as the American Bar Association giving recommendations on TCP window size. And that's true, but we've got to run this through at some point. And it'd be interesting to see how it goes. Beg your pardon. So, briefly now, if you would like to improve your DNS privacy, probably the best and easiest way to go at the moment is find a dot. Do dot. It will at least stop your name lookups being visible to a casual passerby. And if you want to know more about DNS privacy in general, dnsprivacy.org. Now, in the interest of full disclosure, I have to tell you that dnsprivacy.org is a wiki what is run by the people that I work for these days. However, that's all I wanted to talk about for now. But that's what's happening, that's what's coming. And a lot of this is probably going to depend on which way Firefox end up jumping. As I've said, I think what's going to happen is Google and Chrome are just going to go with the Google answer, which is essentially treat it how things are at the moment and just probe for an official one. Okay? This may be something that gets Firefox banned from every corporate network in the planet. I don't know. I don't know whether Firefox will reckon that's a good thing or a bad thing. Anyway, sorry, I've whittled on too long and it's lunchtime. Any final questions?
So, question about Doe.
Yeah.
There's a bit of a chicken and egg problem here because you're making a DNS request.
Yes.
Correct. To a domain name.
Yes.
So, I'm assuming that there's going to be some sort of enforcement of the name so that they can do that.
Yeah, I mean, as I said, there's confusion in here at the moment where, sort of all the proposals for finding out where your DOE server was involve doing an insecure lookup on the existing DNS. To me, this doesn't quite make sense, and it's why actually I think that doing DOE queries to whatever address you're using for your resolver and seeing if that works is actually the way things are going to end up happening. It just makes much more sense to me. It would be nice, perhaps, if there was some bit more privacy guarantees about what you're getting as your resolver, but at least it's kind of under your control. Sorry.
It's using TLS security mechanism, I guess. So I hope they are verifying the certificates on that side, and you can say, okay, I start from there, and the lower level maybe.
Yeah, Yeah, as I was saying earlier, yes, it will definitely check. DOT will carry on, even if they don't match, and there's an open question about what reporting is appropriate from that point, because DOT in Opportunistic is just trying to do the best it can for you. So it will drop all the way back to TCP over port 53. Whatever. No, because there's no way it can drop back. Or rather, as I said, the RFC says you must run this to an HTTPS URL. And indeed, unless you do it, as I said earlier, unless you do it with HTTP2, the HTTP overhead is going to do terrible things for your performance. The Firefox trial that they did last year, they reckoned that using DOE increased their query lookup time by about 6 milliseconds, which I think in any other context would have been deemed unacceptable. But there's something a bit funny. It just feels like there's something a bit funny going on. I heard a rumor, and I won't go further than calling it a rumor recently, that BT had looked at this and said, oh, how can we become a trusted recursive resolver? How can we get on the list of organizations that Mozilla will accept and program into Firefox? And they approached Mozilla and were told that no, BT is too small an organization. What? As I was saying, it all got shoved through very quickly. There's something there's something I can't quite grasp in that. But anyway, yeah, sorry.
So in the end, one of the questions that will come out of this is, what do we trust?
Yes.
Because right now we have DNS, we have DNS security,
Yeah.
relying on having a key that we
Yeah.
look up somewhere. We have DNS over HTTPS.
Yes. Yeah.
Which means we get DNS secure by being on a secure HTTPS connection.
Yeah.
And a secure HTTPS connection can be looked up in the DNS repository.
Yeah.
At the point where just cycling back to the original problem, how do we get the root key that will sign that everything is secure, and then get something that's secure and verified?
I mean, if you want to, if you want to verify the information you begin in is correct, then DNSSEC is the way to go. Definitely. I think this just raises a whole load of questions about, at the end of the day, you have to trust somebody. But the problem is the questions involved are complex, and they don't have an easy answer that's applicable even to one individual all the time. One thing that Mozilla haven't been clear about, incidentally, or haven't clarified yet, is they've said that what TRR you get is going to be region dependent. But sort of under what circumstances? What, when you first connect? Is it going to somehow detect when you're moving around? When's this going to change? And that sort of thing. So it's really sort of, the interesting thing here is a move of essentially the standard, a move of where you're getting one of your standard fundamental services from, being hoiked away from the place you're getting it at the moment to something that may be better or may be worse.
It almost feels like we take the list of CAs that we have that we're basically bothered by, because there's
Yeah.
the Chinese government on there, there's the Dutch government on there.
Oh, absolutely.
There's a whole bunch of governments that have
Yeah.
their own CAs which we don't want to trust.
Yeah.
For Google.com.
Yeah.
And now we're moving to a TRR, which is a list of new companies doing exactly
The same thing, yeah. Yeah, exactly. It just seems to me that who you trust depends on who you are and where you sit. And so so for example, if I'm in an internet cafe or something, my God, I'll use Quad 8, yes. If I'm at home, as it happens, I don't use, I've got Virgin Media at home, and I don't use their resolver, but the reason for that is I think my network works a lot faster if I don't use the Virgin resolver. I think it's just virtually useless at running DNS resolvers or something like that. But yeah, it's, and as it happens, I know this is a very strange thing to say, but I do kind of trust Google myself. Although, in fact, these days I'm mostly using Quad 9, I think, because a lot of the chat I've seen from, a lot of the announcements I've seen about what they support have come from their chief, who seems, I can't remember his name, but he seems to me somebody who's really has got his head screwed on very well. As I said, they're a non-profit as well. Because, of course, one of the other questions is, why are big organizations giving this service away for free? That's not something big companies generally make a practice of doing. Yeah. We come back to... Yeah. Well, except... there's a whole other discussion, incidentally, about this, which was... raised by a report from Jeff Houston, who's the chief research scientist for AppNIC, who is great fun. But he pointed out that, okay, so we got upset about the internet for surveillance. Okay. Actually, the internet is surveillance. It's private surveillance. That's why Facebook is free. The corporations are doing surveillance on the internet to a scale that no government even dreams of at the moment. And that's another discussion that possibly we need to have at some point. But free is always good. That's the problem. Anyway, yeah, sorry.
So, Jim, thanks for the eye-opening talk. The question is, I've been working within organizations that does the man-in-the-middle attack already.
Yeah.
Probably because of that reason. So what would be the team guys at Google, at Mozilla, that you need to engage with to get your organization talking to them? Is there like a...
I'm sorry, I have no idea. I'm just this little sort of programming peon at the bottom of the, at the bottom of the food chain. So, but anyway, and yes, now come on, we're going to miss, the Gannets will have finished lunch by now. So please, if you'd like to carry on talking about it, I'll be around. And